All right, so look at the test for independence and homogeneity. Okay, so the chi-square for homogeneity, okay, is designed to determine whether two categorical data are related. Okay, so like in parametric test where you have to look at association between data using Pearson correlation, or let's say uh, yeah, Pearson correlation is okay, and then some other techniques. All right, here you would actually have to use the test for independence and homogeneity. Okay, all right. So the data values necessary for this test are displayed in a cross classification format called a contingency table. Okay, so these kind of questions are put in a contingency table. So we've seen this in statistical analysis. Okay, so the contingency table gives arrangement of categorical data into a two-way classification. Okay, so it gives this is an example. This R by C contingency table. That's the number of rows and then the number of columns. Okay, so you have your category 1, the various categories here, and then category 2, the various categories also here. All right, and then there are frequencies. So remember the chi-square goodness of it is more like frequencies, the categories, and their frequencies. So this is that. So remember that you are testing for independence. Okay, so we are doing chi-square goodness of it and independence. So now you are trying to, there are two categories, let's say gender and then examination result. Okay, so this is gender, this is the exam result. So you want to see whether gender and exams results have something to do with them in common. Are they related? Okay, that is what you want to see. So your null hypothesis would not assume anything. He doesn't know whether there is something that's going on. So he will just tell you that the two categorical data are independent. Means if you are male doesn't mean you get more marks. If you are female doesn't mean you get more marks. That means your marks doesn't depend on your sex or your gender. Okay. That because you have no idea, so that's always your null hypothesis. And then the alternative will be that the two categorical data are not independent. That means you are saying they are dependent. It means that somebody maybe with gender of male may have more marks than that. Yeah, so you want to verify. Okay, remember that category 1 and category 2, you find the total. This will be the total frequencies for each of the columns, and then the total frequencies for each of the rows will be displayed here. Okay, and then n is here, and that will be the sum. Okay, when you sum this and sum that, it should give you the same thing. All right, and then the test statistic is the same, almost the same as the first one, but just that here we have a row and a column. Okay, so here for this we'll find the expected frequency for this, expected frequency for that, expected frequency for that. So all the frequencies will have their expected frequencies, so we take the difference and square, divide by the expected frequency for each, and we sum. Okay, that is what has been given in this formula. All right, and then now how do we get the EIs? Remember in the chi-square goodness of it, EIs was found by multiplying n times some probability. But here, this is how you get your EIs. All right, the row sum and then the column sum over n. That will give you expected frequency. Okay, your row sum and your column sum over n. So we'll look at that. And then for here, through the degrees of freedom is this: the number of rows minus 1. All right, and the number of columns minus 1. You multiply. So these are the things, you write them down, jot them down. Okay, write them down. So decision rule is the same thing. You reject the null hypothesis if chi-squared is greater or equal to chi-squared alpha degrees of freedom. So take note of that too. So the two categorical data are related. Okay, when you reject the null hypothesis, you say they are related. It's the same as saying they are dependent or they are not independent. Okay, so what's the difference between chi-square goodness of fit, chi-square independence, and then homogeneity? So for homogeneity, so test for homogeneity results when the column or the row totals of this table are predetermined. Okay, so here the difference between chi-square homogeneity and then chi-square goodness of fit is that for goodness of fit, they don't fit anything. We don't say that we are going to take 10 males or maybe we're going to take 10 males, maybe 20 females. We don't fit any value. Okay, but for homogeneity, the row total, assuming this row total may be fixed. Okay, these values may be fixed, whilst even before starting to know the column total, these row totals may be fixed. That will be what will be done in chi-square homogeneity. That's the only difference, but the whole procedure in testing the hypothesis is the same thing. Okay, so example, this is an illustration. This is an illustration of the contingency table. So there is reason to believe that high income families usually send their children to private schools and low income families often send their children to public school. To verify this, 1,600 families were selected at random from a community, and the following results in the table below obtained. So you could see that the two categories are income levels. Okay, either you are low, high, or low, high. That there are only two levels, so low, high, and then schools, the kind of school, either a public school, a private school. Okay, so this is chi-square homogeneity. Then we say that we selected, maybe they will fix this. Either they selected 500 private school students and then maybe 600 public school students. They will fix that values, or they can fix, they selected 1,000 low income people and then 600 high income people. That means they fix that. That is chi-square homogeneity. Okay, all right. So this is a contingency table. So if you see that this is frequency for children who are coming from low and then they go to public school, they are 506. Children with low income level and go to private school, 494. Children with high income level that goes to public school, 438, and then private school with high income, 162. So these are the frequencies, observed frequencies. So what we have to do is to find the expected frequency. Okay, so remember, finding expected frequency, we said row total. So if I are looking at this value, the expected frequency of this guy, the expected frequency of this guy, that means you have to consider the row that this guy is in. This is the row, so this is the row total. Okay, times the column total, so it is in this column. This is the column total. All right, divided by what? N. Divided by n. That would be the expected frequency. Then you add it to this, the expected frequency. So you do the same thing here. The row total is this guy, but the column total remains this, divided by n. That will also give you that. All right, and you get all your expected frequencies. When you finish, you just do frequency, observed frequency minus expected frequency squared divided by expected frequency. Do the same thing to that, do the same thing that when you finish, you sum the results. That will be the chi-square value, okay, that you will use in your test. So that is that. So this is a typical example. Okay, the personal manager of a firm attempted to determine whether an employee's educational level had an effect on his or her job performance. Okay, so to achieve this, an examination was given to a sample of 120 employees. right? So 120 employees, they are all in total 120. Instead of using the examination scores, the manager rather rated each employee's performance as high, average, or low. So these are the educational background or level. So you want to see the two categories are educational level with their job performance, that is same as in exams performance. So he found out that frequencies, PhD students with high performance were only 4, with average were 20, with low it was 11. Bachelor degree with average performance was 22. Okay, so row totals are given and then column totals are also given. So these are the observed frequencies. These are the observed frequencies. Okay, these are the observed frequencies. These are the observed frequencies. So what you have to do is to find the expected frequency. So find the expected frequency for this, for that, for this guy. Find the expected frequency for them. Okay, their expected frequencies, find it, and it's easy. How to find the expected frequency is easy. So if you are trying to find the expected frequency of this, look at the row total, this value, O times column total. So this is a column this guy is in it, divided by n. Okay, that will be the expected frequency for this. If it is this one, the row total is that, column total is 25 divided by that. If it is this, row total is that, column total is that, divided by that. That will give you your expected frequencies. So when you finish, you have to just do fi, this is fi minus the expected frequency all squared. Okay, you have to do fi, okay, fi minus ei, or this guy squared divided by ei. Okay, so this will be your ei. So when you pick 4 minus what the value you get over squared over ei, okay, you do the same for all of this. When you sum, you get a chi-square value. Okay, all right, hope I'm making sense. So that is that. So you want to see that does the job performance as measured by the examination appears to relate. So are you saying that your job performance and your educational background, are they dependent or independent? Test at alpha is 0.05. So state the hypothesis: the employee's job performance is independent of his or her educational background. All right, so note the hypothesis. The two categories or classification, educational level and job performance, are dependent. So opposite of independent is what? Dependent. So always the null hypothesis is independent, and then the alternative is what? Dependent. Take note. So we have to find all the expected frequency. I've showed you how to get these guys. All right, so you can get all the expected frequencies and you draw your table. So when you draw a table, you have your, all the expected frequency has been attached. So you just go and find your test statistic. 4 minus 7.29, so 4 minus 7.27, or 80 root 9, I think there's a mistake, squared over 7.29, here to 20 minus 17.50 all squared, 17.5. So you sum everything. Alright, you get 4.6659. Degrees of freedom, we said number of rows minus 1 times number of columns minus 1. So how many rows? There are 3 rows, 3 columns. So minus 1 means 2 times 2, 4. And then you go and look for degrees of freedom of 4. Alpha is 0.05. So on the chi-square table, degrees of freedom is 4. Alpha 0.05. Degrees of freedom 4. Alright, I think is this the value? 9.488. So 9.488. You compare, this is far less than that, far less, so you fail to reject. Okay, we fail to reject H naught and conclude that there is no evidence of relationship. Now that you are failing to reject H naught, it means you are accepting, you are in a way going with the null hypothesis, which is saying that they are independent. Okay, so there's no evidence of relationship between job performance as measured by the examination and then the level of education. Okay, so that's job performance is independent of educational level of employees. Okay, so this is a typical example 2, which of course you can go through. This is easy, you can go through and then you'll be fine. Okay, so this is a special way. We'll talk about this in the next video. Okay, so have a great day.